Hi, my name is Florian and this is my lab report video for Lab 1 Constant Velocity. The purpose of this lab is to observe motion of an object traveling at a constant velocity without changing direction and compare the experimental and computational models of the position of the object over time. The fundamental principles covered by this lab are Newton's first and second law and the momentum principle. Newton's first law states that an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by an external force. Then we have Newton's second law, which states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The second law is also equivalent to the momentum principle, which states that the net force acting on an object is equal to the rate of change of its momentum. In this lab, because our object is assumed to be moving at a constant velocity with no change in speed and direction, this means that acceleration is zero and therefore our net force is going to be zero. For the formulas, once again we have Newton's second law, force equals mass times acceleration, or change in momentum over change in time. From the momentum principle, we can derive the momentum update formula, which from this we can derive the velocity update formula that we're going to be using, in which we have the final velocity is equal to the initial velocity plus net force over mass times change in time. This formula helps us to make sure that our velocity remains constant with a net force of zero. We also have the average velocity formula, change in position over change in time, which we're going to use to calculate the initial velocity of the object using our first two data points from tracker. And from here, we can also derive the position update formula. Final position is equal to initial position plus average velocity times the change in time to predict the object's position over time. Here's a brief overview of our experimental results from tracker. As we can see from the graph that is showing the object's position over time, the object moves with an almost constant velocity with an almost perfectly linear slope. This shows how the object experienced almost zero net force, which aligns with Newton's first law. For this lab, I chose a toilet paper roll for my system, and the surroundings include everything else that interacts with it, including air resistance and friction from the table surface. The experimental model is generated in Tracker, and the computational model is built using GlowScript. For our procedure, I first captured a video of the object rolling at a constant speed with no change in direction. Then I analyzed the video using Tracker to track the object's motion in frames at constant time intervals. Next, I created a computational model in GlowScript to see the object's predicted position over time. Finally, I plotted both the computational and experimental data in Excel to compare the results. For the initial conditions, I started at frame 17, which is when the paper roll started moving smoothly, and by placing the coordinate origin at the center of the roll on this frame, the initial position coordinate is practically zero. Then I used the first two data points to calculate the initial velocity using the average velocity formula. For the computational model, the given mass in the starter code is 1, and in the velocity update formula, because the net force is 0, the mass would cancel out, and that's why I didn't change the mass because it would not matter in our case. Then I put the initial position and initial velocity I've calculated previously. Our delta t is 0.3 seconds. The iPhone originally recorded the video at 60 frames per second, but to avoid data tracking becoming redundant, I set playback frame rates to 10 frames per second and step size of 3 frames. The net force is 0 here because it's constant velocity, and because our tracking window from frame 17 to 92 covers exactly 75 frames, that's equal a total observation time of 7.5 seconds. Here's a position time graph that compares the results from the two models, and generally we see that they're very similar, but over time we see them deviate from each other, and we can explain this by some potential sources of error. First of all is external force, because in GlowScript we don't account for external forces in real life such as air resistance or frictional force, and another source of error comes from human error while tracking. Moving on to the additional questions, if positive x and negative x axis were interchanged, it would mean that all position values would become negative, which results in a negative slope. But the magnitude of the slope remains constant because the object is still moving at a constant velocity. For the second question, the answer is no. Constant velocity and net force of 0 only tells us that the all the forces cancel each other out. However, there are definitely real-life external forces such as gravity, normal force, friction, or air resistance, and thus the net force of zero does not tell us about these individual forces. And in conclusion, the computational and experimental data are very similar despite a small deviation, and this demonstrates that our object travels with a relatively constant velocity under a net force of zero, which supports Newton's law of motion.